So today we're going to continue trigonometry and we're going to do lesson 2 on unit circles. So last time we had a really basic glimpse on unit circles, what they are, how you use them, how they redefine trig functions. Like now you can use sine, cosine, tangent for obtuse, reflex, angles, etc. Today we're going to take a look at the properties of the unit circle and trig functions in the advanced side. So let me just draw a unit circle. So this is the y-axis, and then let me draw the x-axis. This is the x-axis, and let me just, make a circle. And I'll remove the fill for it so that it's see-through and we can draw. So let's just zoom in on this. So the first property is that, the first property is that sine theta is equal to sine theta plus or minus 2 pi k, given that k is an integer. So why is this true then? So what does this mean firstly? It means that for sine theta, it's equal to it's equal to theta, the angle theta, plus or minus any multiple of 2 pi, or any multiple of 360. Now why is this true? Because notice that if I have any angle here, like this angle here, let's say this is my theta. If I add 2 pi radians to this, what I'm doing is I'm adding this much. So what I end up with is again the same line over here. And I end up with the same coordinates. So the sine, cosine values and even tangent values are still the same. And even if I rotate this more times, I still end up with this point over here as my final value. So the sine, cosine values just don't change, and also the tangent values won't change either, because the tangent base is based on the sine and cosine. So this rule actually applies for both cosine and tangent values. So you can change this to cosine and tangent, and this property will work. Now property number 2 is that sine theta equals, cosine pi over 2 minus theta. What does this mean? So let me draw a different theta here, because this theta looks too much like 45 degrees or pi over 4 radians, which isn't good enough for our example. Let's draw that. Let's say theta is pi over 6 radians or something like that. So sine theta, which is the y coordinate for this, is equal to cosine pi over 2 minus theta. Now what's pi over 2 minus theta then? Pi over 2 is this angle. And pi over 2 minus theta would be something like this. If you can imagine that, it would be something like this. So this would be the sine, cosine values for pi over theta. So this is cosine not pi over theta, pi over 2 minus theta. So what you can do here is that prove the congruency of 2 right triangles, and you can prove that the coordinates are equal. So these 2 right triangles, this triangle and this triangle, are equal, so are congruent, because we know that firstly the hypotenuse is both 1. Secondly, we know that so this angle is theta, and this angle is also going to be theta. Why? Because this here is pi over 2 minus theta, and this is pi over 2. So this is gonna be theta. So there's like the angle, side angle thing. So this is congruent. So since the two triangles are congruent, and if we label the point, so if I label this A, or actually I'll just label it O because it's for the origin. O, A, B, C, D. We know that triangles OAB and triangles OAB and like OAB and COD are congruent via ASA, or angle side angle. So this basically means that AB is equal to OD. So we draw this up here, AB equals OD. So this is actually just the y coordinates for this. So this is actually just the y coordinates for this point, and this is just the x coordinates for this point. And we also know that OB equals CD. So OB is the x coordinate for this point, or cosine pi over 2 minus theta. And CD is the y coordinate for this point, or sine theta. So since these two are equal, sine theta is equal to cosine pi over 2 minus theta. Let me just move these properties over somewhere. So I'll move them over here. Wait. And let me just make them smaller for space. Okay, so what this is telling us is that we know that this property is true, and we also know from this that the cosine theta, which is supposed to be here, so the x coordinate OD is equal to the y coordinate AB. So this is supposed to be sine pi over 2 minus theta. So basically, cosine theta also equals sine pi over 2 minus theta. And another property here that is pretty easy to ignore but is actually kind of important is the Pythagorean theorem property. So we know that. So let's just keep these sides. We know that this side plus this side, so if we draw this side over here, we know that this x coordinate plus x coordinate squared plus the y coordinate squared would give us the hypotenuse, which is just 1. So like we know the side length here is going to be cosine theta, and this side is going to be sine theta. And cosine theta squared plus sine theta squared is going to be 1. So that's an important property that we can use. And another property would be that, so another property would be that this the sine of theta, sine theta would be equal to negative, so sine theta, which is basically this length over here, this red length over here, which is sine theta, would be equal to negative sine theta plus pi. Because like theta plus pi is just this new angle over here, right? And this is just negative theta plus pi. over here. So that's that, and it's pretty obvious that this is true. You can prove that these two right triangles are again congruent to each other, but I'm not going to do that here. And we also know that cosine theta is negative cosine theta plus pi. Like, that's again pretty obvious. It's just like, it's as if this triangle is mirrored by, it's like this triangle over here is mirrored by the origin. So then there's this new triangle with all negative coordinates, because this triangle is in the third quadrant. Like, this point is in the third quadrant, so it has negative coordinates. So that's about the properties, and there's also some other properties that we'll cover next time.